In this lecture, we continue our discussion of continuous random variables. We will start by bringing conditioning into the picture and discussing how the PDF of a continuous random variable changes when we are told that a certain event has occurred. We will take the occasion to develop counterparts of some of the tools that we developed in the discrete case, such as the total probability and total expectation theorems. In fact, we will push the analogy even further. In the discrete case, we looked at the geometric PMF in some detail and recognized an important memorylessness property that it possesses. In the continuous case, there is an entirely analogous story that we will follow, this time involving the exponential distribution, which has a similar memorylessness property. We will then move to a second theme, which is how to describe the joint distribution of multiple random variables. We did this in the discrete case by introducing joint PMFs. In the continuous case, we can do the same using appropriately defined joint PDFs and by replacing sums by integrals. As usual, we will illustrate the various concepts through some simple examples, and also take the opportunity to introduce some additional concepts such as mixed random variables and joint cumulative distribution functions.
In this segment, we pursue two themes. Every concept has a conditional counterpart. We know about PDFs, but if we live in a conditional universe, then we deal with conditional probabilities and we need to use conditional PDFs. The second theme is that discrete formulas have continuous counterparts in which summations get replaced by integrals and PMFs by PDFs. So let us recall the definition of a conditional PMF, which is just the same as an ordinary PMF, but applied to a conditional universe. In the same spirit, we can start with a PDF, which we can interpret, for example, in terms of probabilities of small intervals. If we move to a conditional model in which event A is known to have occurred, probabilities of small intervals will then be determined by a conditional PDF, which we denote in this manner. Of course, we need to assume throughout that the probability of the conditioning event is positive, so that conditional probabilities are well defined. Let us now push the analogy further. We can use a PMF to calculate probabilities. The probability that x takes value in a certain set is the sum of the probabilities of all the possible values in that set. And the similar formula is true if we're dealing with a conditional model. Now, in the continuous case, we use a PDF to calculate the probability that x takes values in a certain set. And by analogy, we use a conditional PDF to calculate conditional probabilities. We can take this relation here to be the definition of a conditional PDF. So a conditional PDF is a function that allows us to calculate probabilities by integrating this function over the event or set of interest. Of course, probabilities need to sum to 1. This is true in the discrete setting, and by analogy, it should also be true in the continuous setting. This is just an ordinary PDF, except that it applies to a model in which event A is known to have occurred, but it still is a legitimate PDF. It has to be non-negative, of course, but also it needs to integrate to 1. When we condition on an event, and without any further assumption, there is not much we can say about the form of the conditional PDF. However, if we condition on an event of a special kind, that x takes values in a certain set, then we can actually write down a formula. So let us start with a random variable x that has a given PDF, as in this diagram. And suppose that A is a subset of the real line, for example, this subset here. What is the form of the conditional PDF? We start with the interpretation of PDFs and conditional PDFs in terms of probabilities of small intervals. The probability that x lies in a small interval is equal to the value of the PDF somewhere in that interval times the length of the interval. And if we're dealing with conditional probabilities, then we use the corresponding conditional PDF. To find the form of the conditional PDF, we will work in terms of the left-hand side in this equation and try to rewrite it. Let us distinguish two cases. Suppose that x, little x, lies somewhere out here and we want to evaluate the conditional PDF at that point. So, trying to evaluate this expression, we consider a small interval from little x to little x plus delta. And now let us write the definition of a conditional probability. A conditional probability, by definition, is equal to the probability that both events occur divided by the probability of the conditioning event. Now, because the set A and this little interval are disjoint, these two events cannot occur simultaneously, so the numerator here is going to be 0, and this will imply that the conditional PDF is also going to be 0. This, of course, makes sense. Conditioned on the event that x took values in this set, values of x out here cannot occur, and therefore the conditional density out here should also be 0. So the conditional PDF is 0 outside the set A, and this takes care of one case. Now the second case to consider is when little x lies somewhere inside here, inside the set A. And in that case, our little interval from little x to little x plus delta might have this form. In this case, the intersection of these two events, that x lies in the big set and x lies in the small set, the intersection of these two events is the event that x lies in the small set. So the numerator simplifies just to the probability that the random variable x takes values in the interval from little x to little x plus delta, and then we rewrite the denominator. Now, the numerator is just an ordinary probability that the random variable takes values inside a small interval, and by our interpretation of PDFs, this is approximately equal to the PDF evaluated somewhere in that small interval times delta. At this point, we notice that we have deltas on both sides of this equation. By cancelling this delta with that delta, we finally end up with a relation that the conditional PDF should be equal to this expression that we have here. So to summarize, we have shown a formula for the conditional PDF. The conditional PDF is 0 for those values of x that cannot occur given the information that we are given, namely that x takes values in that interval. But inside this interval, the conditional PDF has a form which is proportional to the unconditional PDF, but it is scaled by a certain constant. So in terms of a picture, we might have something like this. And so this green diagram is the form of the conditional PDF. The particular factor that we have here in the denominator is exactly that factor that is required, the scaling factor that is required, so that the total area under the green curve, under the conditional PDF, is equal to 1. So we see once more the familiar theme that conditional probabilities maintain the same relative sizes as the unconditional probabilities, and the same is true for conditional PMFs or PDFs, keeping the same shape as the unconditional ones, except that they are rescaled so that the total probability under a conditional PDF is equal to 1. We can now continue the same story and revisit everything else that we had done for discrete random variables. For example, we have the expectation of a discrete random variable and the corresponding conditional expectation, which is just the same kind of object, except that we now rely on conditional probabilities. Similarly, we can take the definition of the expectation for the continuous case and define a conditional expectation in the same manner, except that we now rely on the conditional PDF. So this formula here is the definition of the conditional expectation of a continuous random variable given a particular event. We have a similar situation with the expected value rule, which we have already seen for discrete random variables in both the unconditional and in the conditional setting. We have a similar formula for the continuous case, and at this point you can guess the form that the formula will take in the continuous conditional setting. This is the expected value rule in the conditional setting, and it is proved exactly the same way as for the unconditional continuous setting, except that here in the proof we need to work with conditional probabilities and conditional PDFs instead of the unconditional ones. So to summarize, there is nothing really different when we condition on an event in the continuous case compared to the discrete case. We just replace summations with integrations, and we replace PMFs by PDFs. Let us now look at an example. Consider a piecewise constant PDF of the form shown in this diagram. Suppose that we condition on the event that x lies between a plus b over 2, which is here, and b. So we're conditioning on x lying in this particular red interval. What is the conditional PDF? The conditional PDF is going to be 0 outside the interval on which we are conditioning. So the conditional PDF is 0 in this range, and also it is 0 in this range. Within the range of values of x that are allowed given the conditioning information, the conditional PDF must retain the same shape as the unconditional one, and the unconditional one is constant in that range, so the conditional PDF will also be a constant. Because in this case the length of this interval is half of the distance between b minus a, so the length of this interval is b minus a over 2. In order for the area under this curve to be equal to 1, it means that the height of this curve has to be equal to 2 over b minus a. The conditional expectation in this example is just the ordinary expectation but applied to the conditional model. Since the conditional PDF is uniform, the conditional expectation will be the midpoint of the range of this conditional PDF. And in this case, the midpoint is 1/2 the left end of the interval, which is a plus b over 2, plus 1/2 the right endpoint of the interval, which is b, and so this evaluates to 1/4 times a plus 3/4 times b. We can also calculate the expected value of x squared in the conditional model using the expected value rule. According to the expected value rule, it's going to be an integral of the conditional PDF, which is 2 over b minus a multiplied by x squared. And this integral runs over the range where the conditional PDF is actually non-zero. So it's an integral that ranges from a plus b over 2 up to b. And this is an integral which is not too hard to evaluate, and there is no point in carrying out the evaluation to the end. We now revisit the exponential random variable that we introduced earlier and develop some intuition about what it represents. We do this by establishing a memorylessness property, similar to the one that we established earlier in the discrete case for the geometric PMF. Suppose that it is known that light bulbs have a lifetime until they burn out, which is an exponential random variable. You go to a store and you are given two choices: to buy a new light bulb or to buy a used light bulb that has been working for some time and has not yet burned out. Which one should you take? We want to approach this question mathematically, so let us denote by capital T the lifetime of the bulb. So time starts at time 0, and then at some random time that we denote by capital T, the light bulb will burn out, and we assume that this random variable is exponential with some given parameter lambda. In one of our earlier calculations, we have shown that the probability that capital T is larger than some value little x falls exponentially with that value x. We are now told that a certain light bulb has already been operating for t time units without failing. So we know that the value of the random variable capital T is larger than little t. We are interested in how much longer the light bulb will be operating. And so we look at capital X, which is the remaining lifetime from the current time until the light bulb burns out. So capital X is this particular random variable here, and it is equal to capital T minus little t. Let us now calculate the probability that the light bulb lasts for another little x time units. That is, that this random variable capital X is at least as large as some little x. That is, that the light bulb remains alive until time t plus x. We use the definition of conditional probabilities to write this expression as the probability that capital X is bigger than little x. On the other hand, capital X is t minus t, so we write it this way. T minus t is bigger than little x, and also that t is bigger than little t, divided by the probability of the conditioning event. Just write this event in a cleaner form, capital T being larger than little t plus x and being larger than little t, again divided by the probability of the conditioning event. And now notice that capital T will be greater than little t and also greater than little t plus x. That is, capital T is larger than this number and this number, if and only if it is larger than this second number here. So, in other words, the intersection of these two events is just this event here, that capital T is larger than little t plus x. Now we can use the formula for the probability that capital T is larger than something. We apply this formula, except that instead of little x, we have t plus x. And so here we have e to the minus lambda t plus x divided by the probability that capital T is bigger than t. So we use this formula, but with little t in the place of little x, and we obtain e to the minus lambda t. We have a cancellation, and we're left with e to the minus lambda x, which is the final answer in this calculation. What do we observe here? The probability that the used light bulb will live for another x time units is exactly the same as the corresponding probability that a new light bulb will be alive for another x time units. So, new and used light bulbs are described by the same probabilities and they are probabilistically identical, the same. Differently said, the used light bulb does not remember and it is not affected by how long it has been running. And this is the memorylessness property of exponential random variables. Let us now build some additional insight on exponential random variables. We have a formula for the density, the PDF, and from this we can calculate the probability that t lies in a small interval. For example, for a small delta, this probability here is going to be approximately equal to the density of t evaluated at 0 times delta, which is lambda times e to the 0, which is 1, times delta. What if we are told that the light bulb has been alive for t time units? What is the probability that it burns out during the next delta time units? Since a used but still alive light bulb is probabilistically identical to a new one, this conditional probability is the same as this probability here, that a new light bulb burns out in the next delta time units. And so this is also approximately equal to lambda delta. So we see that independently of how long a light bulb has been alive, during the next delta time units, it will have a lambda delta probability of failing. One way of thinking about this situation is that the time interval is split into little intervals of length delta. And as long as the light bulb is alive, if it is alive at this point, it will have probability lambda delta of burning out during the next interval of length delta. This is like flipping a coin. Once every delta time steps, there is a probability lambda delta that there is a success in that coin flip, where success corresponds to having the light bulb actually burn down. And the exponential random variable corresponds to the total time elapsed until the first success. In this sense, the exponential random variable is a close analog of the geometric random variable, which was the time until the first success in a discrete time setting. This analogy turns out to be the foundation behind the Poisson process that we will be studying later in this course. We now continue with the development of continuous analogues of everything we know for the discrete case. We have already seen a few versions of the total probability theorem, one version for events and one version for PMFs. Let us now develop a continuous analog. Suppose, as always, that we have a partition of the sample space into a number of disjoint scenarios, 3 scenarios in this picture, more generally n scenarios in these formulas. Let x be a continuous random variable, and let us take b to be the event that the random variable takes a value less than or equal to some little x. By the total probability theorem, this is the probability of the first scenario times the conditional probability of this event, given that the first scenario has materialized, and then we have similar terms for the other scenarios. Let us now turn this equation into CDF notation. The left-hand side is what we have defined as the CDF of the random variable x. On the right-hand side, what we have is the probability of the first scenario multiplied again by a CDF of the random variable x, but it is a CDF that applies in a conditional model where event A1 has occurred. And so we use this notation to denote the conditional CDF, the CDF that applies to the conditional universe. And then we have similar terms for the other scenarios. Now, we know that the derivative of a CDF is a PDF. We also know that any general fact, such as this one, that applies to unconditional models, will also apply without change to a conditional model, because a conditional model is just like any other ordinary probability model. So let us now take derivatives of both sides of this equation. On the left-hand side, we have the derivative of a CDF, which is a PDF, and on the right-hand side, we have the probability of the first scenario, and then the derivative of the conditional CDF, which has to be the same as the conditional PDF. So we use here the fact that derivatives of CDFs are PDFs, and then we have similar terms under the different scenarios. So we now have a relation between densities. To interpret this relation, we think as follows. The probability of falling inside a little interval around x is determined by the probability of falling inside that little interval under each one of the different scenarios, and where each scenario is weighted by the corresponding probability. Now we multiply both sides of this equation by x and then integrate over all x's. We do this on the left-hand side and similarly on the right-hand side to obtain a term of this form. And we have similar terms corresponding to the other scenarios. What do we have here? On the left-hand side, we have the expected value of x. On the right-hand side, we have this probability multiplied by the conditional expectation of x, given that scenario A1 has occurred. And so we obtain a version of the total expectation theorem. It's exactly the same formula as we had in the discrete case, except that now x is a continuous random variable. Let us now look at a simple example that involves a model with different scenarios. Bill wakes up in the morning and wants to go to the supermarket. There are two scenarios. With probability 1/3, a first scenario occurs, and under that scenario, Bill will go at a time that's uniformly distributed between 0 and 2 hours from now. So the conditional PDF of x, in this case, is uniform on the interval from 0 to 2. There's a second scenario that Bill will take a long nap and will go later in the day. That scenario has a probability of 2/3, and under that case, the conditional PDF of x is going to be uniform on the range between 6 and 8. By the total probability theorem for densities, the density of x, of the random variable, the time at which he goes to the supermarket, consists of two pieces. One piece is a uniform between 0 and 2. This uniform ordinarily would have a height of 1/2. On the other hand, it gets weighted by the corresponding probability, which is 1/3. So we obtain a piece here that has a height of 1/6. Under the alternative scenario, the conditional density is a uniform on the interval between 6 and 8. This uniform has a height of 1/2 again, but it gets multiplied by a factor of 2/3, and this results in a height for this term that we have here, which is 1/3. And this is the form of the PDF of the time at which Bill will go to the supermarket. We can now finally use the total expectation theorem. The conditional expectation under the two scenarios can be found as follows. Under one scenario, we have a uniform between 0 and 2, and so the conditional expectation is 1, and it gets weighted by the corresponding probability, which is 1/3. Under the second scenario, which has probability 2/3, the conditional expectation is the midpoint of this uniform, which is 7, and this gives us the expected value of the time at which we goes. So this is a simple example, but it illustrates nicely how we can construct a model that involves a number of different scenarios. And by knowing the probability distribution under each one of the scenarios, we can find the probability distribution overall, and we can also find the expected value for the overall experiment. We now look at an example similar to the previous one, in which we have again two scenarios, but in which we have both discrete and continuous random variables involved. You have $1 and the opportunity to play in a lottery. With probability 1/2, you do nothing, and you're left with the dollar that you started with. With probability 1/2, you decide to play the lottery, and in that case, you get back an amount of money which is random and uniformly distributed between 0 and 2. Is the random variable x discrete? The answer is no, because it takes values on a continuous range. Is the random variable x continuous? The answer is no, because the probability that x takes the value of exactly 1 is equal to 1/2. Even though x takes values in a continuous range, this is not enough to make it a continuous random variable. We defined continuous random variables to be those that can be described by a PDF, and we have seen that in such a case, any individual point should have 0 probability. But this is not the case here, and so x is not continuous. We call x a mixed random variable. More generally, we can have a situation where the random variable x with some probability is the same as a particular discrete random variable, and with some other probability it is equal to some other continuous random variable. Such a random variable x does not have a PMF because it is not discrete. Also, it does not have a PDF because it is not continuous. How do we describe such a random variable? Well, we can describe it in terms of a cumulative distribution function. CDFs are always well defined for all kinds of random variables. We have two scenarios, and so we can use the total probability theorem and write that the CDF is equal to the probability of the first scenario, which is P, times the probability that the random variable y is less than or equal to x. This is the conditional model under the first scenario. And with some probability, we have the second scenario, and under that scenario, x will take a value less than little x if and only if our random variable z will take a value less than little x. Or in CDF notation, this is P times the CDF of the random variable y evaluated at this particular x plus another weighted term involving the CDF of the random variable z. We can also define the expected value of x in a way that is consistent with the total expectation theorem, namely define the expected value of x to be the probability of the first scenario, in which case x is discrete, times the expected value of the associated discrete random variable, plus the probability of the second scenario, under which x is continuous, times the expected value of the associated continuous random variable. Going back to our original example, we have two scenarios, the scenarios that we can call A1 and A2. Under the first scenario, we have a uniform PDF, and the corresponding CDF is as follows. It's flat until 0, then it rises linearly, and then it stays flat, and the value here is equal to 1. So the slope here is 1/2. So the slope is equal to the corresponding PDF. Under the second scenario, we have a discrete, actually a constant random variable, and so the CDF is flat at 0 until this value, and at that value we have a jump equal to 1. We then use the total probability theorem, which tells us that the CDF of the mixed random variable will be 1/2 times the CDF under the first scenario plus 1/2 times the CDF under the second scenario. So we take 1/2 of this plot and 1/2 of that plot and add them up. What we get is a function that rises now at a slope of 1/4. Then we have a jump, and the size of that jump is going to be equal to 1/2. And then it continues at a slope of 1/4 until it reaches this value, and after that time it remains flat. So this is a simple illustration that for mixed random variables it's not too hard to obtain the corresponding CDF, even though this random variable does not have a PDF or a PMF of its own. In this segment we start a discussion of multiple continuous random variables. Here are some objects that we're already familiar with. But exactly as in the discrete case, if we are dealing with two random variables, it is not enough to know their individual PDFs. We also need to model the relation between the two random variables, and this is done through a joint PDF, which is the continuous analog of the joint PMF. We will use this notation to indicate joint PDFs, where we use F to indicate that we are dealing with a density. So what remains to be done is to actually define this object and see how we use it. Let us start by recalling that joint PMFs were defined in terms of the probability that the pair of random variables x and y takes certain specific values, little x and little y. Regarding joint PDFs, we start by saying that it has to be non-negative. However, a more precise interpretation in terms of probabilities has to wait a little bit. Joint PDFs will be used to calculate probabilities. And this will be done in analogy with the discrete setting. In the discrete setting, the probability that the pair of random variables falls inside a certain set is just the sum of the probabilities of all the possible pairs inside that particular set. For the continuous case, we introduce an analogous formula. We use the joint density instead of the joint PMF, and instead of having a summation, we now integrate. As in the discrete setting, we have one total unit of probability. The joint PDF tells us how this unit of probability is spread over the entire continuous two-dimensional plane. And we use the joint PDF to calculate the probability of a certain set by finding the volume under the joint PDF that lies on top of that set. This is what this integral really represents. We integrate over a particular two-dimensional set, and we take this value that we integrate, and we can think of this as the height of an object that's sitting on top of that set. Now, this relation here, this calculation of probabilities, is not something that we are supposed to prove. This is rather the definition of what a joint PDF does. A legitimate joint PDF is any function of two variables which is non-negative and which integrates to 1. And we will say that two random variables are jointly continuous if there is a legitimate joint PDF that can be used to calculate the associated probabilities through this particular formula. So we have really an indirect definition. Instead of defining the joint PDF as a probability, we actually define it indirectly by saying what it does, how it will be used to calculate probabilities. A picture will be helpful here. Here's a plot of a possible joint PDF. These are the x and y axes, and the function being plotted is the joint PDF of these two random variables. This joint PDF is higher at some places and lower at others, indicating that certain regions of the xy plane are more likely than others. The joint PDF determines the probability of a set B by integrating over that set B, let's say it's this set, integrating the PDF over that set. Pictorially, what this means is that we look at the volume that sits on top of that set, but below the PDF, below the joint PDF. And so we obtain some three-dimensional object of this kind. And this integral corresponds to actually finding this volume here. The volume that sits on top of the set B, but which is below the joint PDF. Let us now develop some additional understanding of joint PDFs. As we just discussed, for any given set B, we can integrate the joint PDF over that set, and this will give us the probability of that particular set. Of particular interest is the case where we're dealing with a set which is a rectangle, in which case the situation is a little simpler. So suppose that we have a rectangle where the x-coordinate ranges from A to B and the y-coordinate ranges from some C to some D. Then the double integral over this particular rectangle can be written in the form where we first integrate with respect to one of the variables that ranges from A to B, and then we integrate over all possible values of y as they range from C to D. Of particular interest is the special case where we're dealing with a small rectangle, such as this one. A rectangle with sizes equal to some delta, where delta is a small number. In that case, the double integral, which is the volume on top of that rectangle, is simpler to evaluate. It is equal to the value of the function that we're integrating at some point in the rectangle, let's take that corner, times the area of that little rectangle, which is equal to delta squared. So we have an interpretation of the joint PDF in terms of probabilities of small rectangles. Joint PDFs are not probabilities, but rather they are probability densities. They tell us the probability per unit area. And one more important comment. For the case of a single continuous random variable, we know that any single point has zero probability. This is again true for the case of two jointly continuous random variables, but more is true. If you take a set B that has zero area, for example, a certain curve, suppose that this curve is the entire set B, then the volume under the joint PDF that's sitting on top of that curve is going to be equal to 0. So, zero area sets have zero probability, and this is one of the characteristic features of jointly continuous random variables. Now let's think of a particular situation. Suppose that x is a continuous random variable, and let y be another random variable which is identically equal to x. Since x is a continuous random variable, y is also a continuous random variable. However, in this situation, we are certain that the outcome of the experiment is going to fall on the line where x equals y. All the probability lies on top of a line, and a line has zero area. So we have positive probability on a set of zero area, which contradicts what we discussed before. Well, this simply means that x and y are not jointly continuous. Each one of them is continuous, but together they are not jointly continuous. Essentially, joint continuity is something more than requiring each random variable to be continuous by itself. For joint continuity, we want the probability to be really spread over 2 dimensions. Probability is not allowed to be concentrated on a one-dimensional set. On the other hand, in this example, the probability is concentrated on a one-dimensional set, and we do not have joint continuity. In the discrete case, we saw that we could recover the PMF of X and the PMF of Y from the joint PMF. Indeed, the joint PMF is supposed to contain a complete probabilistic description of the 2 random variables. It is their probability law, and any quantity of interest can be computed if we know the joint. Things are similar in the continuous setting. You can easily guess the formula through the standard recipe. Replace sums by integrals and replace PMFs by PDFs. But a proof of this formula is actually instructive. So let us start by first finding the CDF of X. The CDF of X is by definition the probability that the random variable X takes a value less than or equal to a certain number little x. And this is the probability of a particular set that we can visualize on the 2-dimensional plane. If here is the value of little x, then we're talking about the set of all pairs xy for which the x component is less than or equal to a certain number. So we need to integrate over this 2-dimensional set the joint density. So it will be a double integral of the joint density over this particular 2-dimensional set. Now, since we've used the symbol x here to mean something specific, let us use different symbols for the dummy variables that we will use in the integration. And we need to integrate with respect to the 2 variables, let's say with respect to t and with respect to s. The variable t can be anything, so it ranges from -infinity to infinity, but the variable s, the first argument, ranges from -infinity up to this point, which is x. Think of this double integral as an integral with respect to the variable s of this complicated function inside the brackets. Now, to find the density of x, all we need to do is to differentiate the CDF of x. And when we have an integral of this kind and we differentiate with respect to the upper limit of the integration, what we are left with is the integrand, that is this expression here. It is an integral with respect to the second variable, and it's an integral over the entire space from -infinity to +infinity. Here is an example. The simplest kind of a joint PDF is a PDF that is constant on a certain set S and is 0 outside that set. So the overall probability, 1 unit of probability, is spread uniformly over that set. Because the total volume under the joint PDF must be equal to 1, the height of the PDF must be equal to 1 over the area. To calculate the probability of a certain set A, we want to ask how much volume is sitting on top of that set. And because in this case the PDF is constant, we need to take the height of the PDF times the relevant area. What is the relevant area? Well, actually the PDF is 0 outside the set S, so the relevant area is only this part here, which is the intersection of the 2 sets S and A. So the total volume sitting on top of this little set is going to be the base, the area of the base, which is the area of A intersection S, times the height of the PDF, at those places. Now the height of the PDF is 1 over the area of S, so this is the formula for calculating the probability of a certain set A. Let us now look at a specific example. Suppose that we have a uniform PDF over this particular set S. This set has an area that is equal to 4. It consists of 4 unit rectangles and ranged next to each other. So the height of the joint PDF in this example is going to be 1/4. It is 1/4 on that set, but of course it's going to be 0 outside that set. We can now find the marginal PDF at some particular x. So we can fix a particular value of x, let's say this one. To find the value of the marginal PDF, we need to integrate over y along that particular line. And the integral is going to have a contribution only on that segment. On that segment, the value of the joint PDF is 1/4, and we're integrating over an interval that has a length of 1, so the integral is going to be equal to 1/4. But if x is somewhere around here, as we integrate over that line, we integrate a value of 1/4, the value of the PDF, over an interval that has a length equal to 3, and so the result turns out to be 3/4. There is a similar calculation for the marginal PDF of y. For any particular value of little y, to find the marginal PDF, we integrate along this line the joint PDF. The joint PDF is 0 out here. It's non-zero only on that interval, and on that interval it has a value of 1/4, and the interval has a length of 1, so the integral is going to end up equal to 1/4. But if we were to take a line somewhere here, we integrate a value of 1/4 over an interval of length 2, and so the result would be 1/2. So we have recovered from the joint PDF the marginal PDF of x and also the marginal PDF of y. In this segment, we will go very fast through a few definitions and facts that remain true in the continuous case. Everything is completely analogous to the discrete case, and there are absolutely no surprises here. So, for example, we have defined joint PMFs for the case of more than 2 discrete random variables, and we have a bunch of facts about them. In a similar manner, we can define joint PDFs for more than 2 random variables. And if you have understood the material so far, you can guess how such a joint PDF will be used. For example, you can calculate the probability of a 3-dimensional set by integrating the joint PDF over that 3-dimensional set. And there are analogs of all the other formulas that we have here, where we follow the usual recipe. Sums become integrals, and PMFs are replaced by PDFs. Finally, when you deal with a random variable which is defined as a function of jointly continuous random variables, we can use an expected value rule that takes the same form as in the discrete case. And using the expected value rule, we can establish once more the usual linearity properties of expectations. So, absolutely no surprises here. The derivations are either completely straightforward or they follow exactly the same line of argument as in the discrete case with just minor changes in notation. Besides PMFs and PDFs, we can also describe the distribution of a random variable, as we know, using a CDF. A CDF is always well defined, and for the case of a continuous random variable, the CDF can be found by integrating the PDF. And conversely, we can recover the PDF from the CDF by differentiating. There is something similar that happens for the case of multiple random variables as well. we can define the joint CDF as the probability that x and y, the pair xy, takes values that are below certain numbers, little x and little y. So we are talking about the probability of the blue set in this diagram. This probability can be found by integrating the joint PDF over the blue set. And since we're using x and y to be some specific numbers, let us use some different dummy variables to carry out the integration. What is the range of the integration? The first variable, which is s in this integral, ranges from minus infinity up to x. And the other variable, which is the one that we're integrating with respect to in the outer integral, the t variable, ranges from minus infinity to y. Now let us see what happens if we start taking derivatives of this expression. If we take the derivative of this expression with respect to y, what is left is the inner integral. And if we take now a derivative with respect to x of this inner integral, we will be left with just the joint PDF. And it will be the joint PDF evaluated at the particular limits of the integration. So it's going to be f sub xy at little x, little y. So we have this particular formula. By taking derivative with respect to x and then with respect to y, or maybe in the opposite order, it doesn't matter, this particular derivative gives us back the PDF. Let us look at an example. Suppose that we have a uniform distribution on the unit square. So the PDF is equal to 1 on this green square and is equal to 0 otherwise. So in this example, if we take some x and y so that the xy pair falls inside the rectangle, the probability of the blue set is going to be just the probability of that little rectangle here, because everything outside has 0 probability. With a uniform joint PDF, which is equal to 1, the probability is just the area of the set that we're considering. And since this set that we're considering is a rectangle with sizes x and y, the joint CDF is equal to x times y. Now, if we take the derivative of this expression with respect to x and then with respect to y, then we're left just with a constant equal to 1, which is as it should be, so that it integrates to 1. So we have seen that CDFs also apply to the case of multiple random variables, and that we can recover the joint PDF from the joint CDF.